In this video, we are going to learn the functioning of LCR series circuit, for which we are going to use simulator multisim. In one of my earlier videos, I have explained how to log into software multisim and construct circuit on its board. Link of that video is given in the description box. Here I have already constructed circuit with inductor, capacitor and resistor connected in series across an AC voltage source. The value of inductor here is 1 millihenry, that of capacitor is 1 microfarad, which gives theoretical resonant frequency calculated as 1 upon 2 pi root LC equal to 5035 Hertz. The resistance in series is of 200 ohms. We are first going to verify whether this circuit shows resonance at the input signal frequency equal to 5035 Hz as per the theoretical value. For this, initially we will select the frequency to be much smaller. Let's start with a frequency of say 300 Hz. What is the property of resonant frequency? When the input signal frequency is equal to resonant frequency of the circuit, current in the circuit will be maximum, and it is because the potential difference across series combination of inductor and capacitor will become 0 when the frequency of input signal is equal to resonant frequency. The expected value of maximum current in the circuit is equal to 1 volt upon 200 ohms, that is 5 milliampere. The theory of LCR series resonance is explained in detail in yet another video of mine, link of which is also given in the description box. Here, to measure current in the circuit with respect to input signal frequency, we are going to connect current meter in series with this circuit. And to measure the potential difference across series combination of L and C, we are going to connect meter at one end of inductor and the reference meter at the other end of capacitor. This voltmeter is supposed to measure voltage with respect to this reference point. By default, it will give us potential at this point with respect to ground terminal. So to change its reference, we will click on this meter and select the reference coming here to REF1. To make it possible to change the frequency when simulation is on, we will have to make some adjustments over here. To see the current up to its maximum value, we will have to adjust the maximum and minimum values of the current. So let us for time being stop the simulation and adjust the current values. And so we have selected maximum value of current as 5 milliampere and minimum as minus 5 milliampere. We want to observe the waveforms when the simulation is on, and so we will select a split mode. While running the simulation, we would like to change the frequency of input signal slowly. So let's run the simulation. As we have selected triggering on auto, we can change the frequency of the signal continuously. By starting with the frequency of 300 Hz, now we are increasing the frequency of input signal. The blue signal is giving us potential difference VLC, that is across the series combination of inductor and capacitor, and the green dotted signal is giving us current in the circuit. As we go on increasing the frequency, we can see that current in the circuit is increasing and VLC starts decreasing. We have now come to 1 kHz. To increase the frequency further, let's again click on the frequency and increase the frequency beyond 1 kHz. We can see that VLC is dropping and current has come very close to 5 milliampere. Here VLC is almost 0. So resonant frequency is very close to 5.05 kilohertz. This is just a rough estimate of the resonant frequency. The theoretical value of resonant frequency is 5.03 kilohertz, and we are getting the estimated value very close to that. At this particular frequency, current in the circuit has taken maximum value. If we increase the frequency beyond this, current should decrease and VLC should increase. We can observe it happening accordingly. Now we have come to a very large value of frequency, that is 28 kilohertz, and we can see that VLC is much larger than that, around 5 kilohertz, and current has come down below 4 milliampere. Let us now stop this simulation and observe the voltages across inductor and capacitor separately to compare phase difference between them, for which we don't need the current meter. We'll put this reference at the junction of L and C. So the meter 1 will now give us potential difference with respect to REF1, that is potential difference across the inductor. We'll connect another voltmeter to measure potential difference across the capacitor. So that is connected at this point of the capacitor with reference voltage connected to its another end. This meter now should be giving us voltage with respect to REF2. How much phase difference is expected between VL and VC? For any input signal frequency, the phase difference between VL and VC should be equal to 180 degrees. Let us select the frequency beyond resonant frequency, and so we will be selecting it equal to 9 kilohertz. Let's run the simulation to observe the phase difference between the two. Let's stop the simulation, come to grapher mode and expand the time axis, for which we are selecting minimum time as 0 and maximum as 0.4 milliseconds. Let us take minimum voltage as minus 500 millivolt and maximum as plus 500 millivolt. Let us select two cursors along x-axis. C1 is selected to measure potential difference across the inductor, whereas C2 is selected to measure potential difference across the capacitor. C1 is at the peak of the blue curve, which gives us the value here 279.58 millivolt, and the time corresponding to that is 114.87 microsecond, which is indicated over here. Now let us bring cursor 2, which is going to read potential difference across the capacitor at the same time, 114.87 microseconds. This is the position of cursor 2 at 114.87 microsecond, which gives the potential across capacitor as minus 35.33 millivolt. If we shift this cursor a bit, the potential is dropping. That shows that we are right now at the peak, which is negative peak for the potential difference across the capacitor. That means when VL is at its positive peak, VC is at its negative peak. At this, both have come to 0. Again, at this, both have come to 0. And then at this particular point, when capacitor voltage has taken a positive peak value, the inductor takes the negative peak value. This shows that VL and VC are 180 degree out of phase all the time. Earlier, while determining the resonant frequency experimentally, we found that current in the circuit changes its magnitude along with the frequency of input signal. But does this current always remain in phase with Vs? Let us now observe waveform for current in the circuit and Vs, that is the applied voltage, and see the variation in phase difference between these two with respect to the applied frequency. While observing this, we will also observe potential difference across the series combination of inductor and capacitor. For this voltmeter, reference is adjusted as REF1, and so it will now give us potential difference across the series combination of L and C. Whereas for this voltmeter, reference is ground, and so it will measure Vs. Let's run the simulation and observe the waveforms. The pink signal is giving us Vs, the green signal is giving us VLC, and the dotted line in purple color is giving us current in the circuit. To observe these waveforms separately, let us adjust the current with minimum value as minus 5 milliampere and maximum value as plus 5 milliampere. Also observe only 2 cycles, and so we are keeping maximum time as 200 microseconds. Here I have selected cursors for Vs and current in the circuit. Let me keep this cursor at the peak point of Vs. The peak value is 99.71 millivolt, and will keep the cursor for current also at its peak value. The x positions of the two cursors will give us the time corresponding to the peak of Vs and the peak of current in the circuit. Difference in these two in terms of time is shown here as delta x. C1 minus C2 is plus 3.3630 microseconds, which tells us that the Vs is leading the current by the time 3.363 microseconds. So how much is this difference in terms of angle? Let us see how to calculate that. One periodic time of this cycle corresponds to a phase of 2 pi. Periodic time of this signal is equal to 111 microseconds, as we have selected the frequency as 9 kilohertz. One periodic time corresponds to 2 pi, that is 360 degrees, and hence the time of 3.363 microsecond, which is the difference in the peak positions of Vs and current I, shows a phase difference of 10 degrees and 54 minutes between Vs and current in the circuit, where Vs is leading the current. Let us now change the frequency and bring it to a further higher value. So I'll select it to be 20 kilohertz. Let's run the simulation once again and come to the grapher mode. Minimum time as 0 and maximum as 60 microseconds. We'll bring the cursors again corresponding to the peak values of Vs and current. The difference in time corresponding to the peak value of Vs and I is 4.6884 microseconds, which is equal to 33 degree and 45 minutes, where we can still see that Vs is leading the current. This shows that when we increase the frequency and when the frequency is beyond the resonant frequency, the phase difference between Vs and current has increased and Vs is leading the current. Let us now select some frequency below the resonant value, and so let's come down to a frequency of 4 kilohertz. Let's run the simulation and then go to grapher mode. Delta x, that is the time difference between these two peak positions, is minus 7.7151 microsecond, which shows that now current is leading the Vs. Now we'll decrease the frequency to 1.5 kilohertz and run the simulation once again. Let's bring the cursors to the peak values once again. This gives us delta x as minus 43 microseconds, where current is leading the voltage, and earlier when frequency was closer to the resonant frequency, the delta x was smaller. That means phase difference is increasing as we move away from the resonant frequency, and when the input signal frequency is less than the resonant frequency, current is leading the voltage. When the phase difference between current and Vs is changing, is the phase difference between VLC and Vs also changing? Coming to the peak value of VLC, we can see that Vs is leading VLC and the phase difference in terms of time is 122.65 microseconds at a frequency of 1.5 kHz. When we take the frequency of 4 kHz, this phase difference now is 55.391, which is larger than the earlier. We can observe that as we increase the frequency from a low value coming towards resonant frequency, phase difference between VLC and Vs increases, where Vs is leading the VLC. Let us now come to frequency beyond resonant frequency. So I am taking here frequency of 7 kHz, and let's look at the graphs once again. This is the peak position of VLC and here is the peak position for Vs. We can clearly see that VLC is now leading the Vs. Phase difference right now is 35.6 microseconds. We'll increase this frequency further beyond resonant frequency. So let's go to a frequency of 10 kHz. The phase difference now is minus 21.958 microseconds. Earlier at 7 kHz, it was minus 36.608 microseconds. So we have noticed that as we increase the frequency beyond the resonant frequency, the phase difference decreases with respect to the frequency and now VLC is leading Vs. Can we estimate bandwidth of the circuit? Yes, if we can observe the cutoff frequencies, we can. What is the property of cutoff frequencies? At cutoff frequencies, current in the circuit drops to 70.7% of the maximum value. Let us now see how to estimate cutoff frequency of the circuit, for which we need to measure current in the circuit. In our circuit, maximum current is going to be Vs upon R, that is 5 milliampere, and hence when the input signal frequency is equal to cutoff frequency, the current in the circuit should be 3.535 milliampere. To estimate the cutoff frequencies, we'll connect only current meter in the circuit and now we'll keep cursor along y-axis. One of the cursors can be kept to observe the maximum current, where we'll select minimum and maximum currents little beyond the actual values. So we'll take minimum current as minus 5.2 milliampere and maximum at 5.2 milliampere. We'll shift one cursor at 5 milliampere position, which is going to be the maximum current calculated theoretically, and we'll select the position of cursor 2 at 3.535 milliampere. This is the closest that we can select, and that is 3.5306 milliampere. Let's come to split mode, run the simulation. Let's change the frequency from a very low value. Let's go on increasing it, observing the amplitude of current. I'll go on increasing the frequency till the peak of the current wave touches the lower cursor, that is C2. This has just touched the cursor value C2. That means the lower cutoff frequency is coming to 785 Hz. This is the frequency less than resonant frequency at which current in the circuit is 70.7% of the maximum value that will appear at resonant frequency. Now let's go beyond the resonant frequency to find upper cutoff frequency. Current is increasing, it touches the upper cursor, showing that now it is coming to a maximum value of 5 milliampere, and then it starts dropping. We have to now find the frequency which is greater than resonant frequency, where current drops to 70.7% of the maximum value. Here we are very close to the upper cutoff frequency, and that is roughly 32 kilohertz. This gives us an estimate of bandwidth. So what is bandwidth? Bandwidth is the difference between two cutoff frequencies. In this case, it is 31.21 kilohertz. The ratio of resonant frequency to bandwidth gives the selectivity of the circuit. We want to see if we can improve the selectivity, for which we want to see if bandwidth can be reduced by reducing series resistance in the circuit. So we will select the resistance to be 70 ohms and will determine the resonant frequency as well as the two cutoff frequencies of the circuit. The estimated maximum current is now going to be 1 volt upon 70 ohms, and that is 14.3 milliampere. At cutoff frequencies, the current in the circuit is going to be 10.1 milliampere. So let us select the position for cursor 2 at 10.1 milliampere. We'll start with a low frequency. Estimated lower cutoff frequency is 1.95 kilohertz. Here we can see that the current is increasing with frequency, and little beyond 5 kilohertz it is taking maximum value, showing that resonant frequency is still little more than 5 kilohertz. Here the peaks are just touching the lower cursor, and the frequency shown is 13 kilohertz, which will be then the upper cutoff frequency. The bandwidth now is around 11 kilohertz. So we can see that by decreasing the resistance, the bandwidth has decreased, but the resonant frequency has not changed. Thus, the quality factor of the circuit, that is resonant frequency upon bandwidth, will increase with decrease in resistance, making it a good selector circuit. What is resonance curve of the circuit and how it can be plotted? To plot the resonance curve, we need to take readings for the current in the circuit at various frequencies. For example, when the frequency of the input signal is 13 kilohertz, we can measure the current in the circuit, for which we have to stop the simulation, go to grapher mode. We can select the minimum and maximum time so that only 3 to 4 cycles are on the screen. We can observe that current in the very first cycle is a low value, and then it increases and stabilizes thereafter from third cycle onwards. This is because of the back EMF developed across the inductor. And so, while taking readings for the current corresponding to different frequencies of the input signal, we have to observe the current at a we have to observe current corresponding to beyond a cycle where the peak values have been stabilized. Usually it is beyond 5th or 6th cycle. To measure the peak value of current, let us select cursor along x-axis instead of y-axis. Shift the cursor to the peak value, looking at the reading corresponding to the respective cursor. So, to get a smooth resonance curve, we should take readings for various frequencies of the input signal over a range starting from below resonant frequency by 10 and increasing it through resonant frequency up to a value of frequency above 10 times resonant frequency. This is how we can study different aspects of LCR series circuit using the simulator multisim. Thank you.